Okay. So what makes Lagrange multipliers work? And as Arnie, Dr. Vallone used to say, what was Lagrange smoking? Ha ha ha. So I need somebody to volunteer, or I'll volunteer you involuntarily, to be the astronaut flying in space. And in particular, you're going to be a colonel. Okay. So does anybody want to volunteer to be our colonel for this little story? Could be anybody. Don't make me voluntarily volunteer you. Come on, people.
Wait, what was the question again?
Who wants to be a colonel, you know, an astronaut colonel flying in space?
I'll do it.
Okay, Jake, you're it. Colonel Jake. Awesome. Thank you for volunteering. Thank you for your service.
Of course.
Okay, Jake, you're the colonel. You're going to be our astronaut flying in space. So we've got a function, big F, that's a temperature function, and it represents the temperature at any point XYZ in space. And I hear it's awfully cold out there, Colonel, isn't it? Kind of freezing in space?
Absolute zero.
Absolute zero. Ah, okay. Now, imagine that Colonel Jake wants to land on planet X. Okay, now planet X's surface is represented by its own equation. And you know we can represent surfaces with functions that have this look to it. G, we'll call it of XYZ equals 0. This is the representation of planet X. Okay, so that's the surface. It's a level surface. Now we could rewrite it where we, you know, if this were a constant here instead of 0, we could rewrite it where everything is on one side and 0 is on the other, just to make sure we have a 0 on one side. Okay, so Colonel Jake is going to hunt on planet X because he's interested in the point of greatest temperature. He's really freezing right now because he just said absolute 0, and he'd like to warm up. So it's like, where on planet X can I get some heat? So point of greatest temperature. So this fxyz function, we're going to try to look for the maximum of that temperature function. So suppose at point P on the surface of the planet, Colonel Jake finds that the temperature is the greatest. He's like, all right, I found something warm. And so if you were to graph this where time T is along the x-axis and the temp is our vertical axis, remember this is our big F function. So at, say, a certain time, we find a max right there. Woo, right there. Point P gives us a max temp. Okay, so so if you looked at the planet, let's say here's planet X, and let's say here's the point P on the planet. So let's say Colonel Jake, when he located this maximum temperature, he happened to be roving the planet, using some rover, on some curve, C1. Okay, so he's recorded this on the recording device like this. Now, what about a different curve? So let's say Colonel Jake goes, you know, I'm not really convinced that this is really the warmest place on this planet. I'm going to do a different path. So he's like, you know, some other C2 path. And he finds on that path, still this point P is the max. So, you know, on the recording device, once again, here's time T, here's the temp function, which is really big F. And at some time, he records, once again, point P is giving this max on the second curve. It's like, okay, well, shoot, you know, how is this possible? So, you know, maybe he could go on the planet some more, do a whole bunch of paths, you know, and just keep finding that every time he gets this max at the point P. So what about this temperature function? This is big F, XYZ, where XYZ is a point now on the planet. Planet is there. What's the function of time? So I'm going to do one of those schematics, those tree diagrams. Remember the chain rule, guys? So how is the temperature a function of time? We know it's a function of x, y, and z, which are the coordinates of the point in space. But if we let t be time, the independent variable driving the bus, then we can answer this question. So part of the answer is, here is the r of t, x of t, y of t, z of t. This could represent one of the curves. Let's say it represents curve C1 or curve C2. It doesn't even matter. That's your position vector. Plug that into your temperature function. So now you'll have f evaluated at x of t, y of t, z of t, which Arnie used to call the big mother function of time. So once again, if we just kind of look at this, here's this specific time. Here's our temperature. We know we have a max at point P right there. So what do we know at this point? What we know, since it's a max, we know that f prime of t has to be equal to 0, because, you know, that's calculus. You get a max when your derivative is 0. And by the way, why are we doing this again? Why are we involving Colonel Jake and all this? I'm trying to give you a derivation or description of why Lagrange multipliers works. Okay, so that's where we're headed. I'm not just telling a fun story about planet X. I am, but I'm using that to kind of get to a point. There is a point. We're almost there. So if we do the chain rule for functions of several variables, okay, what we're going to have here is what we're saying here, f prime of t is equal to 0. F prime of t, which you could also use the differential type of notation, same as df dt. You guys know the chain rule. You're going to take the partial of f with respect to x, multiply it by dx dt, plus the partial of big F with respect to y times dy dt, plus the partial of big F with respect to z times dz dt. And I'm basically using this schematic up here. You know, you go down this branch of the tree, you have your df dx, and you multiply it by dx dt. And then here we have df dy, and we multiply that by dy dt. And then over here is the partial with respect to z, and multiply that by dz dt. So you just use your diagram to help in case you forget. Now this has to equal 0 because we got this max here. So we have this max, so we got to have it equal to 0. Okay, fine. Now here's the fun part. I love this. Look at this beast over here on the left. Doesn't that look like a dot product to you?
Yeah.
Something times something plus something times something else plus something times something. It has that flavor to it, doesn't it? So which two vectors are we taking a dot product of? Like, you know, it looks like the dot product of a vector with some other vector equaling 0. I don't know. Well, it turns out you're going to have a vector df dx, df dy, df dz, which has another name. It's the gradient of big F. And you're taking the dot product of that guy with x prime of t, y prime of t, z prime of t. And that happens to be the derivative of the vector valued function. It's basically the tangent vector, r prime of t. And you're saying that the dot product of those two vectors is 0. So does this look like a dot product? Yes. So it's the dot product of the vector, the gradient. This is the gradient of f, and r prime, the tangent vector to the curve. Those two vectors, you're taking the dot product. Now, so that's interesting. So what we're saying is whenever Colonel Jake passes through the point P, the gradient of f, that's the temperature function, is always orthogonal. Why is it orthogonal? You guys remember when a dot product of two vectors equals 0, it means they're orthogonal? Yes, no, maybe?
Yes.
I hope so. It's orthogonal to the tangent vector of the path that Colonel Jake is on. Cool. So we know from a previous section that when the gradient for the constraint surface has to always be orthogonal to level surfaces also. So this was a theorem that I went over, and you may have already forgotten it because you haven't maybe had to use the theorem. but it's true. We used it when we find gradients for tangent planes to surface. So you use that fact. So in other words, the gradient for the G, where did I put the G here? Remember G, this was your planet surface. Oh, hold on a minute. Put it back in there. So this is your planet function. So the planet here, this is the representing the planet, his gradient, we'll call it del G, has to be orthogonal to the surface. So what we're saying is that del G also has to be orthogonal to every tangent vector. So not only does the temperature function's gradient have the property that it's orthogonal to every tangent vector, so does the planet's surface representation gradient. So what does that mean? We're saying that both del F and del G, both gradients, are orthogonal to the tangent vector. Can you have both of those orthogonal at the same time? Yeah. Does that mean they're equal? No, but it does mean they're parallel to each other. So, so the picture would be, here's the point P, del G is definitely orthogonal to its own surface here, but we're also saying that the temperature function is also orthogonal to, like, let's say a tangent vector right here, R prime. So both those guys are orthogonal to a tangent vector. Cool. So what we're saying, since they're parallel, and you guys learn this in the first week or two of class, when two vectors are parallel, it means one is a multiple of the other. So it's got to be true that the gradient of F is a multiple of the gradient of G. That has to be true. So this is what we could write. Del F is equal to some constant times del G. That's got to be true. But here's where Lagrange comes in. This constant is basically our Lagrange multiplier instead. So instead of just a C, we use lambda, the Lagrange multiplier. And that's how Lagrange came to be. And that's the story of Lagrange. And that's why it works. So remember that the F function is your quantity to be optimized, and your G function is an equation representing the constraint. So you can only use Lagrange when you have a constraint or more than one constraint. So this is the story, and that's how it came to be. Pretty cool. So in your text, it looks a little different. So the way I did it is I have you create a function of 4 variables. I call it big L, the Lagrange mother of a function. And I have you form it by taking the function that you're trying to optimize, whether it's maximizing or minimizing, and subtracting lambda multiplied by your constraint. And so what happens is when you take all 4 partials and set them equal to 0 and solve the nonlinear system, what you're really doing is you're taking the gradient of F and really setting it equal to some multiple of the gradient of G. I prefer if you do it my way, because you're really extremizing or optimizing big L is what you're doing. So in my mind, you're optimizing this huge function, big L. You're finding his critical points. That's one way of looking at it. Okay. So once you get all your critical points, you don't have to do the d-test. So how do you know which one's the max and which one's the min, if anything? You plug them into the original function that you're trying to optimize, and you see who's bigger and who's smaller. I know that sounds really primitive and kind of cheesy, but that's actually the way you do it. Okay, so I'm going to now do some problems. And one of the problems I want to do, and I want to start with, now that you have the official theorem of the method of Lagrange multipliers, is a problem we already know the answer for. Really? Yeah, I did this problem last time when we found the dimensions of a rectangular box that was sitting flat on the XY plane. You guys remember this one? I'm just going to do it all over again. And the constraint was this plane equation, 6x plus 4y plus 3z. And the box was sitting on the xy plane where one of its vertices was in this plane, like this. I was trying to draw it. Okay, guys, remember this problem? So volume is equal to x, y, z.
Yes.
And then this right here is the constraint. I'm going to do it all over again. And I claim that I want you to notice, especially when you study this stuff over spring break, the two ways of doing this problem. Way number one, which I did when we were looking at the other section, was kind of tedious. I mean, we had to, oops, let me get to, where is it? 252. Let's see. Here it is, 15.7. My absolute extrema. Go back to the problem we did already. Not that one. Not that one. This one right here. Example 10. So we did this problem already. And remember, it was kind of a pain in the rear end because the volume that we were trying to maximize here was a function of 3 variables. So we had to go in and reduce it to a function of 2 variables because you can't, I haven't taught you the d-test on anything but a function of 2 variables. I don't want to get into it. Don't even go there. You want to, come see me in office hours. And so we did have this constraint, and we used the constraint solving it for z, which helped us reduce the volume equation to a function of 2 variables. And then we found the Vx and the Vy, and we set them simultaneously equal to 0. And we found, we actually found a couple of critical points. 0, 0 was kind of one that we didn't want to deal with because we didn't want our box to have 0 dimensions. But then after doing all this hard work, and then we had to do the d-test, and it was pretty involved. So I will tell you that the Lagrange method is not this bad. Now, I'm not going to say you can do it in 30 seconds, but I think that after we get done here and you see Lagrange in action, I will do an informal survey and see which one you guys like, okay? So here in example 2, this right here is your big F. This is the function that we're going to optimize, in this case, maximize. So your big G, if I rearrange this so that it's everything on one side and 0 on the other, he's going to look like this. 6x plus 4y plus 3z minus 24 equals 0. So your big L, your Lagrangian, which is a function of 4 variables, is formed by taking your big F and subtracting lambda, that's your Lagrange multiplier, multiplied with big G. So for us, and this is what I'd like to see on your paper when you do these, xyz minus lambda times parentheses 6x plus 4y plus 3z minus 24. We're going to optimize big L, basically. You're going to find big L's critical points. That's how we roll. Well, how do we do that? Find 4 partials. I thought you said this was easier than the other way. Don't worry. I think it is. And, you know, we'll let you vote. See if which one you like. So when we take the derivative of this whole thing with respect to x, so the derivative of xyz with respect to x is yz minus lambda times the derivative with respect to x rather of 6x plus 4y plus 3z minus 24. And I think that's just going to be 6. And we'll set that equal to 0. Okay. Differentiate with respect to y. That's going to give me xz minus lambda times 4. Set that equal to 0. Differentiate with respect to z now. I get xy minus lambda times 3. Set that equal to 0. And finally, take the partial with respect to lambda. Remember, lambda is a variable we introduced into the whole situation. And as I mentioned last time, I like to think of lambda as the angel from heaven, the helper variable that comes down, helps us out, and then shoots back up to heaven, because usually we never even solve for the lambda. So that's kind of cool. So when you differentiate with respect to lambda, you hold x, y, and z constant. So the derivative of x, y, z with respect to lambda is just 0. And then you're going to have minus, and then this other stuff is a constant multiple of your lambda, and then set it equal to 0. And the L lambda will always be basically your constraint equation. If you multiply both sides by -1, it looks exactly like the constraint. So we're going to solve this the way I told you. Most of the time it works. Not always. And I'll do an example where it's not always. I like to solve for lambda. So there's lambda number 1. And then I'll solve for lambda again. And I'll call that lambda number 2. And then I'll solve for lambda again and call it lambda number 3. So what has to be true? Well, lambda has to equal itself. Like it can't be something different every time. So what do we need? So I need lambda to equal lambda. So how about if we set the first version of lambda equal to the second version? Okay. And what are we trying to do when we do this? Well, what I like to do is I like to get everybody in terms of one variable. For me, I like to get everybody in terms of x. And if you don't like that, then get everybody in terms of y. Whichever one variable is your favorite. Try to get everybody in terms of that one. So here, assuming that z isn't 0, and we don't want z to be 0 because that will be a very uninteresting box that'll have a height of 0. So z not equal to 0, divide out by z, so you kill it off. And then solving for y, multiplying both sides by 6 here, I get y is equal to 6/4 x, and I'll reduce y is equal to 3/2 x. Save that for later. Why is that good? Because now I have y in terms of x. Cool, save it for later. Okay, once again, lambda has to equal lambda, so let's try to set the first version of lambda equal to the third version. This time I'm hoping to get z in terms of x. So let's see what happens here. So again, assume that y isn't 0, so you'll divide both sides by y and basically get rid of it. Solving for z, I get z is 6/3 x, which reduces to 2/3. Now what? I use both of these variables, y equals 3/2 x and z equals 2x, and substitute both into the constraint. That's the next move. So why is that useful? Because then the constraint will have only one variable in it, x, and then we'll be able to get the x and then use that info to get the y and get the z, and then we'll be pretty much done. Yay! So, and then we win the game. And that's the whole point, right? You want to win the game? Well, hopefully, I don't know. So what was the constraint? Well, you know, 6x plus 4y plus 3z, and I'll rewrite it, just equals 24. There's your constraint. That box was constrained by this plane equation. So if I make these substitutions where I found that y is equal to 3/2 x, so I'll substitute that in here, and z was equal to 2x, so I'll substitute that in there. Then what? Well, let's see what happens here. I get 6x plus, and I'll reduce here, that's a 2. Ooh, that's another 6x. That's a 6x. Oh, cool. So now you can combine these like terms, and I get 18x is equal to 24, and then solving for x, and then reducing to lowest terms, oh, I get x equals 4/3. And we already knew that because we know the answer to this one, having done it before. So this is right. Yay! And then what? Well, you know that y was 3/2 x, because that's what we found. So y would be 3/2 times 4/3. And you can reduce that to lowest terms, and I get 2. And then z was twice x, but that's twice 4/3, and that's 8/3. And sure enough, that's what we got last time. So your volume is maximized when your dimensions are 4/3 by 2 by 8/3. And then if you actually figure out your max volume here, it's 64/9 cubic units. They didn't give us the units. So this is your max volume, given those dimensions. And we're done with the problem. I didn't even have to do the D test. Pretty nice, huh? And notice that other critical point, 0, 0, didn't even show up. And remember when we sort of did a rudimentary d-test on that, I think that point 0, 0 turned out to be a saddle point anyway. So it wasn't even a max or a min. So that's why it's kind of not showing up here in Lagrange. So to recap this problem, doing it the alternate method, the method of Lagrange multipliers, you have a function of 3 variables that you're trying to maximize. You do not have to reduce it to a function of 2 variables. Just leave it as a function of 3 variables. That's a real benefit to Lagrange. You don't have to reduce everybody to 2 variables, which is kind of a pain. Leave it. And then you've got your constraint. And with those two equations in hand, basically, you form your big Lagrangian function, f minus lambda g. Take the 4 partials, set them simultaneously equal to 0 to get a nonlinear system of equations with 4 unknowns. But you don't really have to solve all 4 unknowns. You just need the 3 unknowns, because usually nobody asks you to solve for lambda. We could still find lambda if they ask. Well, what if they did ask for lambda? Look, we have 3 equations for lambda, and we already know x, y, and z. So pick one of those, and then you could plug in, and you could easily get lambda if they really wanted it. And sometimes they may ask for it. Economists love to know what lambda is. So then when we solve the system, we ended up getting our critical point, essentially, and that turned out to be a max. Okay, so I'm done with that lovely example. Does anybody have a question or questions? Okay, so let's take an informal survey. If you go to the manage participants or participants on your Zoom, there's 2 little buttons there. One's a yes and one's a no. So use the yes, no buttons and vote. Which one of these methods do you prefer? You can be honest. This is an anonymous survey here. So by clicking on the yes, or if you, which one do you like? Let's have yes be you like Lagrange and no be you don't like the Lagrange method the best, okay? So yes, you like Lagrange, and then no, I like the other method better, so screw Lagrange. Be honest, you know. What's that?
They just did a poll?
Yeah, we're not doing a poll where you're clicking on the yes or the no button.
Oh, okay.
Where are those? Those are where you can go see where your reactions are. So it's just a little area where you can just click on yes or no. Yes or no. Okay, we have 5 yeses and 2 no's so far. Some people aren't even voting. Come on, people. There's 12 people in the room. Go ahead and click on yes or no for me. No? You don't have those reactions, Alan? It might be because you clicked on the Zoom link to get in here and you don't actually have the Zoom app on your desktop or whatever. Maybe we should just do a regular poll. Hey, heck, let's just try one.
The funny thing is that I have like the Zoom app, but it doesn't open it when I do it, so I don't ever get the reactions.
You have to update it.
Update it?
Oh, there you go. You have to update it. Okay. How about this? Let's do a regular poll. So it's, do you understand the concept right now? So I'm just going to hit it. Just try this poll. So do you guys understand Lagrange? Try this poll. Okay. Come on, people, vote. Keep voting. Go ahead. All right. Let's see. I'll end the polling. Looks like everybody got a chance to vote. Let me share you the results. Okay. So there's a couple people who could give a lecture on it, and some of you just need to work out a few points. All right. So, well, let's work out some of those points then. Okay. It looks like most people, well, more people prefer Lagrange. But if you don't, then I'm going to try to make a believer out of you. Let's look at this next example. I love this next example, and you'll see why soon. We're going to do another one of those types of problems where we had Colonel Jake help us out. And Jake, thanks for volunteering again. But suppose this was the temperature function for that whole storyline that I was doing, where I was deriving why Lagrange actually works So this is the temperature function at any point. And let's say the planet was in the shape of an egg. It's an ellipsoid. And let's say this is planet X equation. So if you graph this ellipsoid, it's going to look like, you guys know, it looks kind of like an egg, there's a, you have an egg-shaped planet, fine. And so you've got a temperature function. And so we're going to use Lagrange, and we're going to find the points on the ellipsoid, the planet, that have the greatest and the least temperature. So we want the max and the min. Cool. So what are we saying? We're saying that the gradient of the temperature function, del T, is going to be a multiple of the gradient for this function. If you get everything on one side and 0 on the other, which Lagrange asks you to do. So this, we'll call this big G. So that guy's gradient is a multiple of big T. Okay, so if I form my Lagrangian, it's going to be big T, because that's the quantity to be optimized, minus lambda, that's the Lagrange multiplier. And Lagrange multiplier is multiplied with 16x squared plus 4y squared plus 9z squared minus 144. Okay. So we're going to do calculus on Lagrangian. So I'm going to get 4 partials. Set them simultaneously equal to 0 and hope that I get the answer. Here we go. This T, I'll replace it with what it is, 8xyz. So now when I get the partial with respect to x, I'm going to hold y, z, and lambda constant. So I'll get 8yz minus lambda multiplied with 32x. Set that equal to 0. And while I'm here, let's just solve it for lambda. So I get lambda equals 8yz over 32x. And if I reduce this a little bit, because 8 divided by 32 is 1/4, I'll get yz over 4x. Say that for later and call that number 1. When I get the partial of big L with respect to y, I get 8xz minus lambda times 8y. Set it equal to 0. Solve for lambda. I get 8xz over 8y. Reduce it to lowest terms. And I get, I get xz over y. Call that number 2. Get your third partial here with respect to z. 8xy minus lambda. 18z. Set it equal to 0. Solve for lambda. 8xy over 18z. Reduce it. So my third lambda is going to look like 4xy over 9z. Call that number 3. Your partial with respect to lambda will look like negative the quantity 16x squared plus 4y squared plus 9z squared equal, minus 144. That whole thing equals 0. And that's the same as the constraint as it should be. But that's part of the whole situation. So you still want to do it. Like, I want to see it on your paper. Why? Because it's one of the 4 equations and 4 unknowns here. Because you're going to use it after you get y and z in terms of x. That's how I'm going to roll. So if I set the number 1 lambda equal to the number 2 lambda, because lambda has to be equal to lambda. That has to be true. I'm saying that yz over 4x has to be the same as xz over y. Has to be true. So then what? If I assume z isn't 0, divide out by z, multiply both sides of the equation by 4xy. So I'm going to go like this. I'm doing this all in one shot, like so. And then reduce. So z's cancel, the 4's cancel, the x cancel. And so I'm going to get y squared equals, and on this side, the y's cancel, the z's cancel. And then what do I get? I get 4x squared. So you're trying to solve for y. So if I square root both sides, and keep in mind, I want to see that plus or minus, I get 2 answers for y. And so y is equal to plus or minus 2x. Save that for later. And keep going. So I'm going to set the First lambda I got equal to the third lambda because lambda has to equal lambda. And I have yz over 4x has to be the same as 4xy divided by 9z. That has to be true. Yeah. Okay. So I'm going to try to solve this for z in terms of x. So if I multiply both sides of the equation by 36xz and divide out by y at the same time, and then reduce. So what happens? Well, you know, on this side, after doing all the canceling, I end up with z squared. Over here, well, I get 9z squared, I should say. And over on the other side, I get what? After reducing here, 4 times 4 is 16. The z's cancel. I get 16x squared. Fine. Now what? Now divide both sides by 9. Okay, now what? Take the square root of both sides, but don't forget the plus or minus. Okay, fine. Then I get z could be plus or minus, you know, the square root of 16 over square root of 9 times square root of x squared. And that, after cleaning it up, looks like plus or minus 4/3 x. Okay, now we're ready. You're going to substitute these into the constraint. Now, you have to be careful here, because we're basically saying that y could be plus or minus x, and z could be plus or minus 4/3, 2x, I meant 4/3 x. So when we plug into the constraint, I'm going to kind of honor that. So there's our constraint. That's the ellipsoid equation. And when you square a negative, it'll automatically be positive. So that's what's going to happen there. And then this is going to end up being, after I reduce to lowest terms, and then you can add the terms on the left-hand side since they're like. And wow, I'm running out of room. So let me go and get another page here, because this is turning into a really ridiculous problem. And sometimes they do. So x squared is 144 over 48. Oof, and you can reduce that, but I'm not going to do that yet. Let's do the square root of both sides. Okay. And then I'll get x equals, and it turns out that 48 times 3 is 144. Nice. So x is plus or minus square root of 3. So what does that mean? So y could be plus or minus 2x. So plus or minus 2 square root of 3, and z could be plus or minus 4/3 x. So that's plus or minus 4 square root of 3 over 3. So how many critical points are there? And this is where it gets kind of dicey, like a lot. You're not going to like this. But I claim since x, y, and z can be one of two things, you know, two things, or two things, plus or minus. 2 times 2 times 2 is 8. So there are 8 critical points. Well, who's going to be the max and who's going to be the min? Can I just pick one of each? No, not for this problem, because I claim that 4 out of the 8 will give you a max temp and the other 4 will give you a min. Well, how do you know what? I'm going to show you. So one of the critical points is where everybody is positive. So x is positive, y is positive, and z is positive. Certainly that is going to give you one of the maximums. Why? Look at the equation, or the function that we're trying to see who's the max of. When you substitute your critical points into this temperature function, 8xyz, you want to get a max. Well, since x, y, and z can be positive or negative, I hope you can see that if we can get a positive product, that will give us the maximum points. And you know, a negative times a negative times a negative is a negative. So the critical point where x, y, and z are all negative values will give a minimum temp. But there's other times you can get a minimum. What if only one of them is negative, but the other 2 coordinates are positive? A negative times a positive is a negative. So that'd be another point that'll give a minimum, and so on and so forth. So watch closely here how I kind of divvy them up. I claim that a max temp will be obtained when everybody's positive. Okay. One of the guys is, two of the guys are negative and the other guy is positive. And that will be happening with where X and Y are negative. And how about if we have only X and Z be negative, but Y is positive? And how about where X is positive, but Y and Z are negative? That will give me, all four of those will maximize the temp. And so what is that max temp? Well, you know, just it's going to be the same value for all four of these points. So if I just pick the square root of 3 version and then multiply this all together. So this is 64 square root of 3. And I think they said it was in degrees Celsius. So 64 square root of 3 degrees Celsius, which I believe is approximately 110.85. Ooh, that's pretty hot. Now, what about the minimum temp? Because they asked for min. So I claim that of those 8 critical points, 4 of them will give the same minimum temp. So one of them will, one of the points will happen when all 3 of them are negative values. Another one where X is negative, but the other 2 are positive. Another one where X is positive, Y is negative, and Z is positive. And finally, where X and Y are positive and the Z is negative. So that all 4 of those points will give a minimum temp. And the min temp is just going to be the opposite here. This doesn't always happen, by the way, but it does for this problem. Will be the opposite of 64 square root of 3. And so that's going to be awfully cold. So there's your min temp. So that's a Lagrange multiplier problem. Questions?
Yes, could you scroll up a little bit, please, Professor?
No problem. Tell me when.
A little bit more.
Okay.
A little bit more, please.
Okay, I'm going.
Yeah, right there, I think. Is it?
Okay.
Yeah, right there.
Right there.
Yes.
All right. So to recap, you had a function to be optimized, you had a constraint, you create your big Lagrangian function that involves those 2 equations basically with your Lagrange multiplier stuck into the conversation to help you out. Get your partials, set them equal to 0, solve the nonlinear system, get the critical point or points, and no d-test required. Just figure out who gives the bigger value and who gives the smaller value. And the bigger value is the max and the smallest value is the min. Pretty cheesy, but that's the way it works. Okay, and any other questions or concerns or? All right, so I'm going to do it. Yes? Question? No? Okay, I'm going to move on to the next example, which is a classic. Do you think this kind of thing will be on an exam? Yeah, I mean, these are all possible candidates for a quiz or exam. So I know it's Friday, it's before spring break, and I had a student ask me, well, are there, you know, do you give a study guide or any tips on what's going to be on the exam when you get back from spring break? Because you're going to have an exam. No, study everything. You know, I don't give out like, oh, there's going to be 1 of these, 2 of those, 3 of these, 4 of the other. It's everything's fair game. So how could you study? Well, I'd study everything in your course reader for sure. Because I mean, anything I've done in lecture is like, I consider important. And not just study it, like don't just read it and go, yeah, I'm good. And then flip to the next page. Yeah, I'm good. That's not a good way to study. To me, that's not studying. In STEM, when you're truly studying, you have a piece of scratch paper or many pieces of scratch paper. You cover up the answers that I did for you in lecture and you work the problems fresh and see if you get the right answer. And anytime you get it wrong, put it aside and do it the next day. Again, like keep doing the ones that you keep getting wrong over the course of the spring break, so that by the time the actual exam hits, if I give you something like that, you'll be fine. And I would do that for everything. Well, but you did so many problems in the last 3 weeks or whatever. I know. You've got a lot of sections to cover. We did all of chapter 15 and the last 3 sections of 14, and it is a lot. Be prepared. So, obviously I'm not going to give you 5 problems out of one section. I mean, we did 11 sections. You definitely can count on this. There's going to be at least 1 problem taken from each section. Okay. But that's only 11 problems. And I think I put more than that on the exam. I don't even remember how many problems I put on the exam. I'll just say this, it's less than 20. Okay. So I could have put, 1 out of one of the sections, because, that's not such a biggie a section, but another section, I'll just give you an example of a section I think is a little bit more juicy. The section on directional derivatives and gradients. That was a very juicy section that had a lot of meat to it. Not only finding a directional derivative, but properties of the gradient and things like that in there. So that's something that most likely will have more than 1 problem corresponding to it on the exam. Does that make sense? The juicy ones? Yeah, juicy ones like that. You should really focus on. Another juicy example would be the chain rule section. That's good, because in the chain rule section, not only did you have to know the chain rule, you had to know implicit differentiation. So that one's a little juicy. And the section where you had to do finding the equation of a tangent plane and the parametric equations of a normal line, and that also covered differentials. That's a pretty juicy section. So I would definitely count on more than 1 problem pulled out of that section, just because there's more than 1 juicy concept in that section. Does that help? Kind of focus on,
Yeah.
Juicy is a technical term. No. That's kind of my thinking on how I roll when I create an exam. Okay. It's like going into a buffet. I give you a little bit of everything, like you get to taste all the dishes, and a couple of the dishes you might have 2 helpings. That's all. That's kind of how I roll. Yeah, but none of that dinner tastes good. Oh boy. Okay. So let's use Lagrange multipliers on another problem that's going to seem kind of tough. So watch out. So here's a sphere. And then they're asking us to determine the point on the sphere that's furthest from this point. Now this point is on the sphere. Like if you plug in the point, where is it? No, it's not in the sphere. Sorry. 1, negative, let's do 1, negative 1, 1. 1, negative 1, 1 is like right here. And your sphere is actually, it's centered at the origin of radius 2. So let me try to draw this pretty well. I'm not very good at drawing sometimes in 3D, especially nice spheres. Oh boy, that sphere looks terrible. If you can imagine, this is a sphere of radius 2. Wow, that's pretty poor. But this point is inside the sphere, obviously, but the sphere is hollow. So you want to figure out the point on the sphere's boundary that's the furthest away from this point. So obviously it's not going to be, the answer is not going to be this point over here, because that looks like it'll be the closest point. So it's probably going to be some point over here. We don't know which point, but some point way over here on the opposite side of the sphere will be the point that's furthest from this point. So I'm just trying to get a picture. You don't have to draw a picture to get what's going on here. So what are we trying to do? We're trying to maximize a distance. We're trying to maximize a distance. So if here's the point P and we want, the point that's, we'll call it D here, what's the point that's furthest away? The max distance. So remember the distance between 2 points, you know that formula because that was something we did the first week of class. So I don't know what the coordinates are for the mystery point here. So I'm just going to give the coordinates on the boundary of the sphere, the mystery point, arbitrary coordinates, X, Y, and Z. But I do know the point P coordinates, 1, -1, and 1. So using the formula for distance between 2 points in space, I'll have the square root of x minus 1 squared plus y minus a y minus 1, but that's y plus 1 squared, plus z minus 1 squared. So you're going to need to optimize this. Now, folks, I hate square roots, especially taking derivatives with square roots. It's a pain. So is there an easier way to do this problem? Absolutely. Wouldn't you like to know this little bit of a shortcut? And I'm going to train you right now. And folks, if you took Calc 1, they did this in Calc 1 because I teach maximizing and minimizing distances in Calc 1 also. And I always tell my Calc 1 students, look, folks, don't try to do all the calculus on this square root. It's horrible. Instead, here's something I need you to buy. Maximizing the radicand of this square root. Radicand means the junk underneath the radical will maximize the radical. Do you buy that? Do you buy that? Because I claim it's a fact. If you maximize the stuff underneath a radical, then taking the square root of it, you'll still maximize the square root function too. So that's going to be our plan. We're going to call the function underneath the radical, we'll call it big F, and we'll maximize that guy. And then later on, when they ask us for the actual minimum or maximum distance, we'll plug it back into the original we'll put the square root back on. But let's just look at what's under the radical, because then we don't have super hellacious derivatives to worry about. Yuck. So now in the constraint equation, when we rewrite it, x squared plus y squared plus c squared minus 4 equals 0, this is right here, our big G. And so when we create the big Lagrange, a mother of a function of 4 variables, x, y, z, lambda, is equal to the function that we're trying to maximize minus lambda. Lambda is our Lagrange multiplier. So for us, this function of 4 variables will be the x minus 1 squared plus the y plus 1 squared plus the z minus 1 squared minus lambda times that sphere. The sphere is our constraint because it has to be on the sphere. Okay. So now you know what I'm going to do. I'm going to get 4 partials. Yeah. And set them equal to 0. That's how I'm going to roll. So using the chain rule to help me take the partial of big F with respect to x, I'm going to get 2 times x minus 1 to the 1 times the derivative of x minus 1 with respect to x, but that's just 1, minus, and then I'll have my lambda, times 2x equals 0. And then I'll do the same thing to find the partial with respect to y. I'm going to use the chain rule. So I'll have 2 times the quantity y plus 1 to the 1 minus lambda times 2y. And the partial with respect to z, oops, hold on a minute, that's a minus. And the partial with respect to lambda, which always ends up being really the constraint equation. So you know how I'm going to roll. I'm going to solve for lambda. You guessed it. Oh, yeah. Sure. And after I reduce by canceling out the 2's, I get my first version of lambda looks like that. If I solve for lambda a second time with the other partial, and reduce it by canceling out the y's. So this is version number 2. Solve for lambda again. Reduce. Lambda number 3. Okay. And, you know, if you're bored right now, like, oh, you always do this the same way. Don't worry. I will be doing it a different way. Yeah. So number 1 equals number 2. Lambda has to equal lambda. So what does that say for us? So I get x minus 1 over x has to equal y plus 1, oops, y plus 1 over y. And if I multiply both sides of the equation by xy to clear fractions and then reduce, I'll get y times the quantity x minus 1 on the left. and I'll get x times the quantity y plus 1 on the right. But then if I distribute, and both sides of the equation have that xy term, so just subtract it out. And then I get y equals negative x. Please be careful. This is not saying that y is equal to plus or minus x. That's a different problem. That was the previous problem. But a lot of times I get students who are like, once they watch my lecture, they, erase some of their brain cells and they make silly mistakes. Oh, that's just like the one in lecture. You have to be careful. I purposely put this one in lecture to make a point. It's not a plus or minus. You're saying that y is always the opposite of x, no matter what, not plus or minus for this problem. If I set the first lambda equal to the third lambda, they have to be the same. Lambda has to be equal to lambda. So this time I'm saying that x minus 1 over x is the same as z minus 1 over z. And I'm going to multiply both sides by xz and do the same kind of thing. Here on the left, the x's cancel. Here on the right, the z's cancel. Ooh, hang on. And I distribute. And both of these sides have an xz term, so just subtract xz. And you get negative z equals negative x, but then multiply both sides by negative 1. So now what? Now you plug both of these into the constraint. What's the constraint? The sphere. We're constrained by the sphere. Okay, so you're plugging x for z and negative x for y into your sphere equation, like this. So, but anytime you square a negative, it'll be positive. So you really are getting x squared plus x squared plus x squared equals 4. But that's 3x squared equals 4. Fine. Then you go solve for x. And then you square root both sides, honoring the fact that you're going to have a plus or minus. And I get x will be plus or minus 2 over square root of 3. Now, which gives the max and which gives the min? And this is real tricky because a lot of students don't bother plugging into the original. They guess based on, some sort of hunch. And it's like, not a good idea. The opposite of what you intend. So what are the critical points here? Like, and how many do we have? It's not like the other one where we had a whole bunch. If x is, no, I don't want to do Adobe, sorry. If x is positive, remember y is always the opposite of what x is. So y will be negative. But z is always the same as x, haha. So there's a critical point. The other critical point is what if x is a negative, because x can be plus or minus, okay? But if x is negative, since y is always the opposite of x, oops, not a square root of 2, my bad. Stop trying to write so fast. Y will be the opposite in sign, and then z is always the same sign as x, so he doesn't have a choice. These are the only two critical points. So which one's the max and which one's the min? You got to be careful. Don't guess. Remember that we're trying to maximize the distance here. And this was the distance. And remember, it was the same as maximizing the radicand. So I claim when you plug in the this guy here, the one with 2 negatives in it, this actually gives the bigger value. This gives the max distance. So you can prove it to yourself, like here's the actual distance if they ask for it. You're going to go x minus a minus 2 over square root of 3 squared plus y plus 2 over square root of 3 squared plus z minus a minus 2 over square root of 3 squared. And that gives approximately 3.73. The other point, now they didn't ask us for a minimum distance. So it's like you don't have to give them the other point if they only ask for a max. But I claim that this is going to be, if they did ask for both a max and a min, this point would give you a minimum distance. okay? And I didn't calculate that, but if you plug that into your distance function, you would be able to get some other alternate answer, not negative 3.73. For God's sakes, distances can't be negative, okay? It's some other value. And if you look at our picture that we drew here, we're basically saying that this max distance is 3.73 units. And whatever the minimum distance is, we could find that, but it would be, you know, obviously some smaller value. And that's it for the finding a distance. Any questions on that? So a
Oh,
lot
wait,
of
so-
work. Go ahead.
Wait, so the answer was the equation for D equals just plugging the
Well, there's sort of several parts of the final answer, okay? One of the parts is this is the point on the sphere that will give the max distance, this point with these coordinates. Can you see that?
Yeah.
And then the actual max distance that you get when you take that lovely point on the sphere is this value here. This is the actual max distance. Now, when you're doing a MyMathLab problem homework, sometimes they will ask you for just the point itself for the answer. And sometimes they want the value itself as the answer. And sometimes they want both. So please make sure you read the directions and you give them everything that they want. And don't give them something they don't want. Like if they only wanted you to give the max distance and they didn't care about the point, although I better see the point on your handwritten work. Like there's no way you could have gotten this maximum distance value without first finding the point. But sometimes I see students when they type stuff in on MyMathLab maybe doesn't give you enough direction just to see if you'll hang yourself. I've seen people enter in a vector when they were supposed to enter in a scalar, and vice versa. I've seen students enter in a point when they were supposed to enter in a vector, and you got to know the difference of what it is you're being asked. So just be careful and read the problem very carefully to see what it is that they require. Okay, that's all.
Okay.
Now, you know I give partial credit, so I'm always looking to give you your partial credit points, of course. You know, if I can maximize your test score, subject to the constraint of a student's silly mistakes, that's what I'm trying to do here. Although I don't know if I could use Lagrange method on that. All right, now let's talk about Calc 1. Now in Calc 1, you don't learn the Lagrange method, okay? Because that's too advanced. You don't learn how to do partial derivatives in Calc 1. But I want you to get that the method of Lagrange multipliers can also be used to optimize functions of two variables as well. Now we did the higher power versions of Lagrange, this whole section so far, where we were optimizing functions of three variables. But it'll work for functions of two variables just as well. So if you have a function of xy and you're trying to find a max or a min and you've got a constraint, little g xy equals 0, then the max or min will occur at the critical numbers of that new function, the big lambda. You know me, I like the big lambda, but it'll be a function of three variables, just x, y, and lambda, that Lagrange multiplier. So it looks the same. So you're still going to extremize or find the extrema for this big function. And so what ends up happening when you get all the four, or in this case, three partials, you'll get Lx, which is going to end up being fx minus lambda gx, set that equal to 0. You'll get another partial, fy minus lambda gy equals 0. And then you'll get L lambda, and that'll just end up being minus g of xy equals to 0. You'll solve this system, and that's essentially the same as what the text says. The text says solve this basically where del f equals lambda times del g. And that's essentially what you're doing. Okay? So we're going to do another distance problem because those are classic Lagrange problems, like for reals. So we did the distance from that point to a sphere. Fine. Let's do another distance type problem. I really want you to get it. So here's the point, 0, 3, right there. So there's the point P. And you've got a parabola here, y equals x squared. And they want you to minimize the distance this time. Okay, so what's the minimum distance from this point that's sitting on the y-axis to this parabola? Now I don't know where the point is. You know, let's say it's I don't know. Looks like it might be here. So I'll just give it coordinates x, y. So what's this minimum distance here? Where P has coordinates 0, 3. So you're just going to do the same thing as before. Use your distance formula, and you're going to take the difference between the x coordinates and square it, and then add that to the difference of the y coordinates and square it. Yeah. And then I'm going to ask you to buy the same claim that I asked you to buy last time, that minimizing the radicand will minimize the distance. So I don't have to worry about taking derivatives with square roots. Because that's just nasty. You know, I don't want to. I mean, you can. It'll still work, by the way, if you leave the square root there. But I mean, why would you do that to yourself? Do you like pain? Don't answer that. Maybe I don't want to know. So the function that we're going to try to minimize is the radicand, the stuff under the radical. So my big L, my big mother of a function, is going to be this little f minus lambda times little g. But what is little g? They gave me that y equals x squared. This is your constraint. Can't spell constraint. So if we rewrite it where we get everything on one side and 0 on the other, we can call this y minus x squared. That's the little g. So now when I actually create my big L, I'll have x squared plus the quantity y minus 3 squared minus lambda times my constraint. So I can put my y minus x squared in there. So I'm going to do my best to do the calculus on this big L. So get the 3 partials and simultaneously set them equal to 0. That's an L lambda there. Okay, so when I differentiate big L with respect to x, I'm going to get 2x minus lambda multiplied by negative 2x, and that will set that equal to 0. When I use the chain rule and take the derivative with respect to y, I get this. And when I differentiate with respect to lambda, I basically get the constraint. Now, folks, this is one of those problems where my usual method of getting lambda solved for and then equating my lambdas does not work. Let me repeat that in case you're snoozing. Getting lambda solved and setting them equal, kind of, it's not going to get, it's going to, well, let me put it this way. It'll work, but it won't, it's not sort of the same flavor where you have different things. So just watch closely because it just got a little bit different to it. I don't want you to freak out when this happens, okay? Because otherwise we'll be in trouble. So here, if you rewrite this equation, because you got a minus minus, you really have 2x plus lambda 2x like that. Okay, fine. Let's solve for lambda. Okay, we'll do that. And then I get lambda is equal to 2x over negative 2x. But that reduces to lowest terms. So I don't get an expression for lambda. I get a constant. So this is different. It's got a little different flavor. Please don't freak out and think that you did anything wrong, because sometimes that happens. And it's like, well, what am I going to do now? Don't worry. It's still going to work out. So here, I'm still going to solve for lambda. And I get lambda is equal to 2y minus 3. Okay. Now, these lambdas still have to be equal to each other. I mean, lambda still has to be lambda. I mean, that's not going to change. But if lambda is equal to negative 1, okay, you're basically saying that negative 1 is equal to 2 times the quantity y minus 3. So I'm going to divide both sides by 2. And then I'll add 3 to both sides. And I get y, which if I clean that up a little bit, I think I get y is 5/2. How do I get x? Any ideas?
Set the 1 week.
How to get the x? Any ideas?
Would you plug the lambda and the y to the lx that we used in the beginning?
Okay, so here in the beginning, what am I doing?
And lx?
In Lx? Well, when I did Lx, though, I got lambda is equal to 1. So how's that going to help me get my x?
Can you use L with respect to lambda?
As you plug in the y.
Yeah, you use the constraint, which is basically the key right here. So you're going to go like this. So the answer is use your constraint. And remember your constraint, the easier version of it is just y equals x squared. So what am I saying? If you look at the picture of what we're trying to do, folks, don't lose sight of the actual application. This point, do you get this point has to be living on the parabola itself because that's the way the problem is? Please say yes.
Yes.
Okay, so you know that y, we just got it. It's 5/2. Yeah. So what's the x coordinate going to be? Knowing that you have to be living on this parabola. So if you plug y into the parabola equation, essentially, which is your constraint, so y equals x squared, but you're basically saying 5/2 is equal to x squared. So get the x. Well, you know you're going to square root both sides, but you better not forget your plus or minus. Well, does that mean there's going to be two answers? Yes, you're going to see that in a moment. Watch closely. So what are we saying? The 2 points are going to be square root of 5 over square root of 2, 5/2, and negative square root of 5 over, oops, that's just one negative there. Sorry, I got carried away. 5/2. And both of them minimize the distance. They both give the same minimum distance. Both give the same. One isn't a max and one isn't a min. Both of these minimize. Well, how do you know? Well, you could just plug it into the distance formula that we did at the very beginning of this problem to prove it to yourself. But more important, because that's going to take some time, do you guys notice that this parabola has some symmetry to it about the y-axis?
Yeah.
So wouldn't this point over here with the negative coordinate and the same y-coordinate have the same distance as the point on the other side? So both points are the answer. But they didn't ask us for the points. They just said minimize the distance. So it looks like they don't even care about the points, even though we did all that work. And the actual min distance, which looks like that's what they want, we have to plug this into the distance formula here. So you're going to have x. So if you look at what you had there, you had x squared plus y minus 3, but y is 5/2 squared. Okay, and you do all this. So this is going to look like what? 5/2 plus some funky number here. 5/2 minus, this is minus 6/2. So this is going to be basically a half squared. And you're going to end up, I think, with square root of 11/4, which is square root 11/2. So there's your actual min distance right there. Square root of 11/2. And we're done. That's the answer. That's the minimum distance from that point P03 to the parabola. Okay, any questions on this one? It's another one of these distance ones. I know it's pretty funky, but something that you've never done before, but it's not that bad. If you just follow the procedure, you should be safe. Yeah. This one had a little different flavor because we got a constant for the lambda.
Yeah.
So now I'm going to do a really, 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 really hard problem to finish it out. But before I do, let's do a mean. Sorry, I need a little bit of humor before I do this last problem. I actually saw this meme first when for differential equations, because when you do a differential equation, it usually takes forever, like many pages. So I saw this meme for solving a differential equation. What year is it? And I went to one of those meme generators and did one for Lagrange multipliers. You're welcome. Well, I don't find it that funny. Well, okay, sorry.
So
Let's see. So this problem is going to be one that's on your My Math Lab homework. Or similar, they may just change the numbers. So please focus up because it's weird. You're not going to set the lambdas equal to each other. So watch closely, because the moral of this story is do not set lambdas equal to each other. It won't work. You're going to get totally stuck, and then that's when the tears start, and it won't be pretty. So this is the function to be optimized. So if we form our big Lagrange function of, this case, 3 variables, we'll put that first, minus lambda times our constraint. And you always want to write your constraint where everything is on one side and 0 on the other. Okay, so extremize this function. Okay, you know the drill. You're going to get the partials, and then you'll set them simultaneously equal to 0 and solve the nonlinear system. Okay, fine. I get 8x minus lambda times 2x, set it equal to 0. Then I get 2y minus lambda times 6 plus 2y, and that's it, equals 0. And then when you take the derivative with respect to lambda and you hold x and y's constant, you basically get a version of the constraint. Fine. Now what? Well, here, what you're going to do is you're going to use the ZPP. What? So this will help you. So use the ZPP. What's that? Well, that's when you factor, and you'll get a product equaling to 0, and then you set the factors equal to 0. So when I factor out a common factor from 8x minus lambda times 2x, a common factor is 2x. And I get 2x times the quantity 4 minus lambda equals 0. Oh, God. Now what? Apply to ZPP. You got something times something equals 0. The first something has to equal 0, or the second factor equals 0. Fine. So what are we saying? We're saying x equals 0, or lambda is equal to 4. Or maybe they're both true, but it doesn't matter. Now, you got to be careful here, because we're going to separately substitute these into the other partial. So the plan right here is separately, and that's the key, substitute these into Ly, not both at the same time. Please, please, don't, well, you can, but, well, do we want to do that? No, just watch yourself here. Okay, so now, if you look at Ly, which is right here, what are we going to do? Well, there are no x's, so that's good news. So you're going to substitute lambda equals 4 into this Ly. So I'll have 2y minus lambda, but lambda is now a 4, times the quantity 6 plus 2y equals 0. Fine. So then what? All right. Well, I'll distribute the negative 4. What the heck? So I get minus 24 minus 8y equals 0. But then 2y minus 8y is negative 6y, and then I'll add 24 to both sides. So then if I solve this for y, I get 24 divided by negative 6. But that reduces to negative 4. Now, here's where you got to be careful. It is not true. This is where students blow this whole problem, and then they come crying to me. And remember, I have office hours next week on Friday. But during the week, I may not answer your email right away. Like, I'm probably going to wait till Friday because I'm busy. I'm grading. I'm doing a whole bunch of other crap. Okay. I got to go up to LA. You don't even want to know. Okay. So much stuff. It's horrible. It is not the case that 0, negative 4 is a critical point. Remember when we got x equals 0 up here? But let me just remind you. See where I got x equals 0? A common student mistake is to go, oh, we already got x equals 0. That means when x equals 0 and y is negative 4, that's a critical point. No, No. So what are the critical points? I'm getting there. Just calm down. Okay. Let's plug x equals 0 into the constraint. Okay, well, what's the constraint? I forget. The constraint was x squared plus 6y plus y squared equals 16. If you plug x equals 0 into this guy, what do I get? Oh man, I get a quadratic equation. Oh heck. So how about if I subtract 16 from both sides? Okay, now you could use the quadratic formula right now because you know that always works. But I claim this kind of factors, you know, you can use inspection here. I claim that it factors as y plus 8, y minus 2. Ooh, cool. Use the ZPP. That's your friend. So what am I saying? Y plus 8 equals 0 or y minus 2 equals 0? Well, then I get two answers. Yeah, I know. So what are we saying? We're saying there are two critical points right now that just came up. One of them is when x is 0 and y will be negative 8. The other one is when x is 0 and y is 2. Could you stop there? No, you're not done. Well, what do you mean? Because you remember we got that y equals -4 thing happening? We still have to deal with that. And what's going to happen is that's going to yield, you're going to freak out about this, but that's going to yield two more critical points. So we're going to have 4 in all. It's going to be pretty messy. So what am I saying? So you're going to substitute y equals -4 into the constraint. Oh, wow. Okay. So when I do that, I'm going to get x squared plus 6 times y, but I'm substituting y equals -4, plus y squared, but we're substituting -4 there, equals 16. And then this is going to help me get x. And so the 16s end up canceling. And then if I add 24 to both sides, I get x squared equals 24. And then don't forget, when you square root both sides, you got to do a plus or minus. Oh boy. 24 has a perfect square as a factor 4. So we can, oops, this is going to be x, not x squared, sorry. So x could be plus or minus 2 square root of 6. So there are two more critical points. Oh my God, this is getting really complicated. Yeah, I know. So you'll have 2 square root of 6, -4, or negative 2 square root of 6, -4. So now what do we have? We have 4 critical points total. So what's the deal? Like, you're not going to do the D test. So here's what you have so far. You have 0, -8, 0, 2, 2 square root of 6, -4, and -2 square root of 6, -4. So who's the max and who's the min? So keep in mind, you're trying to optimize this function right here. You're trying to find the max and the min of this guy. And it turns out you're going to have to one by one separately substitute each and every one of these 4 points into this function. And whoever gives the biggest value for the function, he gets to win the maximum. And it turns out that 0, 2 gives the absolute max, or excuse me, absolute min. And so if you, well, what is the value? Well, if you plug in the 0.02, you'll get a 4. So this is the actual min value. It's 4. And then who gives the absolute max? It turns out that either of these points, the 2 square root of 6, -4, and the -2 square root of 6, -4, both, because they both give the same, both give us a max value. So what it, because when you square a negative, it ends up being positive. So it doesn't matter which of these 2 points you substitute into this function, you get the max value. I get 112. So this is the actual max value. What about that other point? You know, remember there were 4 points. that we got, well, he doesn't contribute anything, too bad. He loses the game. He's neither the max or a min, okay? Pretty weird problem, but that's where you're solving a nonlinear system that's a little bit crazy, okay? And that's all I got for you. Congratulations on making it through Lagrange multipliers. We're officially done with chapter 15. And when we get back from spring break, you're going to take an exam. And then after that, we'll get into multiple integrals where we do double and triple integrals. Exciting stuff, people. It's coming.